real quickly introducing the material session. We're focused on carbon and the climate crisis, rightly so, but it's important to remember that we are ultimately protecting biodiversity and healthy ecosystems that provide clean air and water and nutritious food to eat. The focus on climate is important, though, because if we have an unreliable and out of whack climate, that makes all of the other issues, such as ecosystem die-off, spread of disease, water scarcity, exponentially harder to solve. Architecture can actually remove excess carbon dioxide by deploying materials that solidify it from the atmosphere, either by photosynthesis or carbonization. Many of these products are available today and can also contribute to the critical drawdown solution of regenerating soil health. This session will explore the use of materials in the use of these materials in an urban metropolis setting. And an overview will be given by Bruce King, founder and director of Ecological Building Network and author of the incredibly inspiring book, Build Beyond Zero. He'll be followed by 4 15-minute presentations of four materials. The first by Matthew Omalia, co-founder of Timber HP. Then Maddie Mead, founder of Hempitecture, and Louis Grosso, lead inventor of Positive, and Travis Olivier, composite business manufacturer of Aero Aggregates. And Bruce King is on the West Coast, so he's remote.
Thank you very much. I wish I could be there with you, but that wasn't happening this time. Let's do a quick review of the context we're in. For the last 500,000 years or so that our particular family of primates has been evolving on Earth, the carbon dioxide has been more or less steady between 200 and 300 parts per million. And of course, a couple hundred years ago, we went wild when we discovered fossil fuels and discovered all the goodies that go with that. And now the price tag is coming due and we're finding ourselves in dire straits. Last I checked a couple days ago, the count was 419 at Mauna Loa. Here's the thing. Even if we were to stop burning the fossil fuels on a dime today, we would still be in trouble. Common sense and the IPCC tell us that we have to pull carbon back out of the air in addition to stopping the burn. Which brings up the question, where are you going to put it? Right now, the oceans are doing most of the work, all the heavy lifting for us, which is proving to be disastrous for the oceans and oceanic life, which therefore for us and all other life, because everything is based out of the ocean. Where might we put carbon if we draw it out of the sky successfully? Well, the first and probably the best and maybe the biggest repository is soil. And there's all sorts of people, some of them in this room, I'll bet, we're doing work with regenerative agriculture. How do we grow our food and restore the carbon in the soil that we've been depleting over the last couple hundred years? Another one is to pump it underground. That's very popular in certain circles. And right now, the US taxpayer is paying oil companies to pump carbon dioxide into depleted oil fields to replenish them and get more oil and gas out of the deal, and then claim they're doing climate work. Something a little screwy about that scenario. And we're not quite sure about the durability of the carbon down there. It could become a problem later on. Then there's us, architects and engineers, designing buildings and cities at a fast clip. We use more physical stuff than every other industry combined in our construction. And we're doing a lot of construction. In case you hadn't heard, we're building the equivalent of another New York City on Earth every month right now. And if that seems incredible to you as a North American, because you're not seeing it, I have been to each of these 3 cities in the last few years, and each one was jaw-dropping in its energy and activity and the rate of construction. All the activity, all the new New York City every month is happening in Asia, of course, in Africa and South America, not here. But it is happening. Buildings account for about 40% of greenhouse gases. I'm pretty sure you've heard that. It comes in 2 phases. First, you build it, the embodied or upfront emissions from the materials and products you chose and the trucks roaring around, and then everybody moves in, turns on the lights, turns on the HVAC, and over the course of 40 or 60 or 80 years, the operating emissions eventually dwarf the embodied emissions for just about every building type. And so that's what we've been focusing on in green building, right? And that's why you're gathered passive house and net zero movements all over the place. And it's great. And we brought those operating emissions down with great success on at least some buildings to or near zero. Problem is, we have a different context now that we weren't really aware of even 5 or 10 years ago. We're in emergency now. It's not just climate change, it's climate emergency. We're feeling the effects all over the place. I'm in California with the fires. You're getting the hurricanes. Somebody else is getting the floods. It's happening now. What can we do? What can we do in the context of climate emergency? Well, think triage. Think the next couple decades, not the 60 or 80, 100-year lifespan of the building you're designing right now, but the next 10 or 20 years. In that context, things look quite different. And the embodied emissions prove to be much bigger because they're in the air longer. It's not just how much carbon you put up there, it's how long it's in the air. And the embodied emissions are up there cooking us away before you even move in to occupy the building. This is your big takeaway. That number will vary a bit from building to building and type to type, of course. Everything always varies. But the vast bulk of the impact of the project you've got on your boards right now is from the materials and products you choose to build it with, not so much on how effective it is as an operating building. How do we get to zero and beyond? How do we get to regenerative? How do we get to where business as usual is buildings and cities, every one that goes up is taking carbon out of the air rather than putting it in? Two basic categories of building. Minerals and plants. Those are the two categories of stuff we build with. Minerals, it's mostly about concrete. That's by far the biggest. If it were a country, the concrete industry would be the third biggest emitter on Earth after China and the USA. It's huge. And it could flip all the way around in just a generation to be a carbon absorbing entity. I first heard some years ago that we're making something like 10 billion tons a year, mostly the Chinese and the Indians, of course. I got to wondering about the numbers because we see these big numbers, 10 billion tons. Well, your eyes glaze over, you go, yeah, another big number. So I did the math. 1 ton of concrete is desk height. 10 billion tons of concrete is a cube a mile on a side. It's 5 times the height of the Eiffel Tower, and that's what we're producing every year. Pound for pound, concrete is a very low carbon material, but a cubic mile of anything is going to have some impact. Part of how we're going to change things with concrete is by rediscovering the original concrete, clay concrete, also known as earthen architecture. This picture is from a museum in Switzerland where they've rediscovered and played with rammed earth and earthen plasters. Lots of other stuff happening. The Pritzker Prize last year went to the wonderful Francis Carré for his work with natural materials and native materials in his native Africa. Metals and glass are the other two big mineral products we work with. And since they're already operating at a very high recycling rate, you're going to hear more about that in a moment with Positive. Their big bet is on hydrogen. Replace that intense fossil fuel energy, the intense energy that they need to melt glass and metal, and replace fossil fuels with hydrogen, and then replace the hydrogen available today with green hydrogen made from renewable energy. And that's coming on strong. So the gist is we need a whole bunch of infrastructural work so that instead of pipes and ships and trucks hauling fossil fuels all over the place, we're going to be gathering the carbon and have an infrastructure to move it around and use hydrogen for our heat sources with all these industries that need intense heat sources. Then you got plants. Let Mother Nature do the work. Let her gather the carbon out of the air and then use the plants to build with from the forests and from the fields. I think Sarah was trying to touch on this and we couldn't unpack it fully here at all, but you need to understand about plants, whether it's grasses and hays or bamboo or timber and mass timber, that a lot of the carbon is in the ground. A lot of the carbon is out of sight. The plant you see is only a portion of the mass of the plant and the carbon that's being stored in any particular location. So how we harvest those plants matters in the climate picture, because a lot of that carbon's underground. And if we muck it up, we're making more of a climate mess rather than fixing it. Mass timber. Everybody loves mass timber these days, and all sorts of cool buildings are going up. It is cool. We couldn't do this before, but we worked out how to cut the wood and glue it back together in ways that originally was just plywood and then OSB and then glulam beams, and now it's mass timber, and we can do large buildings with mass timber that previously we could only do with steel and concrete. Great, right? Well, not necessarily. It's become a sort of poster child for climate-friendly construction when, in fact, it's not necessarily. And very often when you see a mass timber building going up, what's in the background of it is something like this, because the forest got ravaged in order to get that extra timber. It's not a clear picture at all. It's not black and white anyway. And unable to say more about it right now. Let's just say it's muddied, and at the very least, you should use sustainably harvested lumber when you do use lumber. FSC certified is your best bet. Well, straw, right. The world grows a lot of straw. I told you about that cubic mile of concrete. The world also grows about 1.6 mile cube of straw every year, which is the waste product left over after you've taken the barley and the oats and the rice that we eat. The straw left over, which at great quantity becomes a waste problem for the farmers. If we turned all the current straw harvest in the world into insulation materials and building products, we would negate all the emissions from the concrete industry. Chew on that. We've been building with straw for millennia, actually. It's one of the original building materials, stuffing it into walls and putting it under our beds and so forth. But it sort of had a new beginning with straw bale construction invented in the Americas, in western Nebraska, actually, 120 or so years ago. Very picturesque, and some of those buildings are still there. People went back and studied them, and a renaissance came out of that 30 years ago, and it became this big thing. Straw bale construction still is a big thing, but you're not going to build another New York City out of bales of straw. So what can you do? You can have straw 2.0, and now there are more products than I can keep track of now all over the world using straw as their feedstock. Blocks, insulation systems, spray insulation systems, panels. The French in particular are way ahead of us on this, and doing fabulous buildings, big buildings, routinely all over the place. The British are doing stuff, the Australians, the Canadians. Straw bale construction itself, like those other two American inventions, democracy and jazz, has spread all over the world just on its own merits. People love it. It's a fun way to build. And now it's going urban with straw products that accommodate where you can't have a wall that's this thick, you have to go this thick. What do? This is the answer. And just by the way, you can insulate with cellulose. You're going to hear more about that in a moment too, with wood chips, with wood sawdust, with straw, with hemp. And they all absorb carbon. They store carbon in your building, unlike those spray foams that are emitting huge amounts of carbon with their application, especially the spray ones because of their blowing agents. People sometimes ask us, well, straw, it's going to burn, right? It's going to burn. Well, sure it will if you give it a chance. So will plastic foam. Some of you will remember Grenfell Towers, right? 6 years ago, a bunch of people died. And that wasn't because they used straw in the walls, because they used a petroleum product to insulate the building, which fed the fire. Something about our culture is we think, oh yeah, plastic foam, that ought to be fine, but straw, I can't trust it. Well, making your building out of petroleum products is kind of inherently problematic with regards to fire. We have some bespoke crops that are coming on strong. Hemp, one of my favorites, and again, you're going to hear about that a bunch in a moment, so I don't need to dwell on it. It's just great, though. You can do all sorts of stuff with hemp. There's a reason why it's so popular and why our ancestors used it to make the rope for their sailing ships. It's because among all the plants, it has one of the strongest fiber and aspect ratios at the cellular level of any plant. So you can do all sorts of stuff, and it's very tough and very durable and very strong. Make blocks, make insulation, all sorts of stuff, and many, many products coming online. Likewise, bamboo also grows like a weed, and by itself, you can't do much with that strange, lumpy looking, huge piece of grass. People do, and there's some fabulous architecture going up in South America, Central America, the Pacific region. It's not what you would call affordable housing, but certainly beautiful. Very labor intensive, very lovely. Okay, not relevant to us, right? Well, but then people started playing around with the bamboo, and you take those bamboo columns and you squish them down and glue them together like we do with wood now, and you can make panels. And a company out here in California, Bamcor, is doing that, making these panels that actually have a whole lot of extra energy efficiency. You can build a wall without any studs that are thermal bridges. Possibly the biggest one is microbes, using our little friends, the algae, fungi, and bacteria that we're only starting to learn about to make concrete, to make insulation, to make all sorts of things. And among all the building materials, they stand out. Not because you see them, because you can't see them mostly. But of all these plant products, the microbes stand out for this very reason. My friends did some studying a couple of years back and wanted to know how much carbon could you store per acre, per hectare of land. Well, a softwood forest, 2 to 4 tons. Straw field, 2 to 5. Hemp, oh, looking much better, 22 to 44. Looking real good, right? But then when you look at what the microbes can do, theoretically, nobody's got an acre of microbes growing and creating stuff yet, but people are developing microbial concrete, microbial insulation, microbial, just about everything, glues. And that's where we can really seriously store some carbon. These two categories of materials we've had with us forever. We have had concrete and metals and glass and insulation for centuries, for millennia. They're not new. We've updated them. We've done them better and faster and more efficiently with fossil fuels and all that, but they're basically the same. There's only one new category of materials, which is plastic. So wonderful and so terrible, right? It's everywhere. It's entrenched in our lives. Paleontologists of the future will dig down and find this layer of plastic everywhere and call us the people of plastic. It's surrounding you with hundreds of different polymers in the building you're sitting in. It's on your body. You're wearing it. It brought you the last meal you ate. It's everywhere. The utility is fabulous. And the horror of it is starting to become clear to us because it won't go away. You throw it away. You think you're recycling it. It ends up in a landfill. It ends up in the river. And it ends up in the ocean. Then it breaks down and it chokes all the little ones, all the life, all the plankton that are the basis, as we now know, of life on Earth. What do we do about that? We could have a whole day about that, couldn't we? And there's lots of people working on it, but please be conscious, please be sparing. I did a project here in the Bay Area with a wonderful Silicon Valley power couple who were really great people, and they wanted to build the greenest possible house. And among other things, they had a goal of no plastic, and we couldn't do it. We couldn't do it. We could eliminate in a lot of places, but the insulation on the wires and a few other places, we couldn't have all the goodies that everybody expects with a building without the plastic. So we've got a big job on our hands replacing that. And I think with that, I'm done. I wish I could be there, but thank you.
Thanks, Bruce, for the presentation. And we have Matthew here.
Hi, everybody. It's great to be here. My name is Matt O'Malia, and I am an architect, executive partner at Opal Architecture, Opal Build, and a co-founder of Timber HP. My background, as I said, I'm an architect. So how I got into the profession is I wanted to build beautiful buildings. I was interested in space and light and composition, probably all the reasons that you guys joined the profession as well. But as I got into it and I learned and sort of developed my understanding of what buildings meant to the environment, I realized that just building a beautiful building isn't enough. We have to be really focused on the impact those buildings have, because we as architects, as we're discussing here today, have a really outsized impact on the environment. And taking that seriously is obviously extremely important. So as I developed, I realized we really had to focus first and foremost on emissions, which is why We certified and built the first passive house in Maine, the 12th in the United States back in 2008. So that was really early days for the North American passive house movement. All these buildings you see here are pacified, certified, close to the standard or net zero. That's all we do and that's all we build. But we also realized the more we got into it is passive house is great on operational carbon, but there's a lot more to the story. And that's just what Bruce so eloquently described and the previous speakers. So as we were very focused on building lovely buildings to the passive house standard, we realized that it's time to focus on the materials that we're using to buildings with as well. So as I'm getting on to the three companies that I have, Opal Architecture, that's the work that you saw. Timber HP, we're a startup and we're manufacturing insulation from the residuals of the lumber industry, so the waste stream of the lumber industry. And Opal Build is a CLT panelization company, sort of the love child of Opal Build and Timber HP. This statistic is widely known, and I think it's been shown at least 3 or 4 times today. Buildings emit a lot of carbon in the atmosphere, 1/3, 2/3, operational embodied. That's why I started in passive houses, probably you all did as well, which is a great solution to reduce operational carbon as the baseline for net zero construction. We can take pride in the fact that this has adopted a hockey stick curve adoption in the marketplace and has really influenced conversation and policy around the country, which I think is critical to move that forward, particularly on goals to net zero. This is a statistic by the AIA 2050 goal net zero buildings, which means that our cumulative carbon over that time period will level out to zero as defined by net zero in terms of carbon. That's a huge victory. When I started in 2008, I never would have believed it would be possible, but I do think it's possible. But as Bruce also said, the embodied carbon of all those New York cities that we're building year after year is going to be equivalent to that savings of operational carbon from here going forward. So we really do have to focus on the materials and the carbon in the materials that we're using to build our buildings. When we started looking at the project, I'll lie, I won't lie, I wasn't interested in embodied carbon. I was interested in the human health of the installers that were putting the materials up. I had a design build company and I was constantly getting complaints about what insulation is like to install, and I took that seriously. But when you look at the detail here, this is a statistic by RMI, Rocky Mountain Institute. You'll see that insulation has the greatest opportunity for carbon reduction. Why is that? Because insulation, A, is not sexy, and B, is a dumb material. It has one job to do, keep the warm in, the cold out. It can be made from a variety of feedstock materials, glass, fiberglass, steel slag, oil, or biogenic recyclable materials. So when we're talking about the conversion to a biogenic economy, we're talking about where the low-hanging fruit is, and replacing insulation is a really, really good starting place with a great opportunity with no additional cost. This is a slide we're all probably familiar with. We saw Grenfell already burning today. We know I've already complained about the installation issues of insulation, but it's also non-renewable, non-recyclable, in many cases toxic. So when we're looking at the carbon footprint specifically, it's really about the question of what are the viable biogenic sources that we can replace these insulations that are scalable and cost competitive. The other thing that insulation does, as we all know in the passive house community, is save energy or save carbon. The fact is, with a carbon storing or negative material, you come to the job site carbon negative from day one. When you have high carbon footprint materials listed on the right there, it takes a certain period of operational carbon savings to pay back that carbon footprint. I think we all agree we have a climate imperative, and 10 years of carbon savings to pay back the original footprint of those materials probably isn't going to work for us. It's probably not an acceptable solution. We have to be carbon negative day one. Timber HP, that's co-founder, and myself, Josh Henry. He's a PhD chemist. I'm an architect. An unlikely collaboration. It sounds like the beginning of 2 guys walked into a bar, architect and the chemist, then pa. That's us. But nonetheless, we looked at this opportunity around wood fiber insulation. It's an above grade suite of insulation, a blown-in product replacement for cellulose, a bat product, press fit cavity, and a continuous exterior board insulation, renewable, recyclable, carbon storing, thermal performance competitive, and importantly, particularly the board product is like a Gore-Tex. It's windproof, it's waterproof, but it's vapor permeable. Instead of putting a continuous exterior insulation such as plastic, which is impermeable, wood fiber insulation breathes, allowing it building more durability and better moisture management. Can be used in a variety of applications, thermal and acoustic. Its density gives it high STC classification similar to mineral wool. It has a long track record in Europe. It's been there about 20 years. It's about 10% of the market right now of the European insulation products. It's growing rapidly because of the carbon story. But the trouble with it is until recently, it wasn't manufactured domestically. So we're coming from the state of Maine, where we have incredible forest residuals. And by the way, most of our forests are FSC certified, so sustainability is a high priority. But what we're doing with wood fiber insulation is we're not cutting the trees. We're taking the byproduct, the waste stream from the lumber industry, those little chips coming out of creating dimensional lumber out of round logs. That's about 50% of the tree right there. That used to be diverted to paper mills. In the state of Maine, we lost 8 paper mills since 2016. That was a net negative impact on our economy of $1.6 billion annually. Unlike New York, Maine is not a very rich state. And that really, really hurt our industry. So there we have residual piles. And when we started Timber HP back in around 2015, 2016, those are softwood residuals, which are the feedstock for wood fiber insulation. We were wondering, why the heck isn't wood fiber insulation produced domestically when we have this massive, inexpensive reserve that we could create a value-added product, not only creating a solution for buildings, but also rural jobs and supporting the lumber economies. Maine, as I said, is highly certified. We have a regeneration rate which really justifies increased use of forest products. And that story repeats itself across the United States. It's not just Maine, it's Oregon, it's the upper Midwestern states that have lost paper manufacturing, and a great opportunity to sort of revitalize rural economies and jobs in forest states. And then now this isn't really working. All set. All right, so there it is. In 2019, we bought an abandoned paper mill. So this is a great example of recycling infrastructure. 600,000 square feet. We've been in the process of reconfiguring it to a wood products manufacturing facility. We'll be employing 125 people. It's a large manufacturing facility. On site is 225 megawatts of hydropower. So we're very close to net zero in terms of our operational energy. As you can see, it's large scale industrial manufacturing. You really can't do a small wood fiber insulating manufacturing plant. That's the inside of the paper manufacturing facility. And the carbon story around it is when you're looking at the insulation in the standard construction, just looking at the insulation products using one of our bats relative to some of the existing products on the market, you can see a savings, which is relatively impactful on one house. But when you consider that we're building 1 million houses a year in this country, not to mention all the retrofits, that really starts to add up as a beneficial solution. We're just talking about the replacement of insulation here. The second thing is when we're thinking about passive house cold climate, we're getting it in Maine up to an R50 wall. The continuous exterior insulation then has another significant impact. This is just the walls, is not insulating the roofs and ceilings and so forth. So again, it's a really sort of promising story on the opportunity around carbon savings just by the replacement of high carbon footprint materials. We're in production with our loose fill product, which has taken a lot of blood, sweat, and tears to get up and running in a very expensive project. We're actually starting the bat line production next week, which is great. And then our board will come into the market early next year. So they will be available in the marketplace. In terms of utilization, the bat and the loose fill are Class A, so they're treated with boric acid, about 4% by weight total, which obviously extends their use into a variety of construction types. The board is Class B. Originally, when we're starting construction, we'll have a Class A board, which I know is relevant to a lot of you folks building projects here in New York. So thank you all.
Good afternoon, everybody. My name is Matthew Mead. I'm the founder and CEO of Hempitecture. It's good to see some familiar faces in the audience, a lot of new faces as well. Thanks for being here today. I'm the founder and CEO of Hempitecture, and we are a building materials company that is pioneering innovative carbon negative building materials using industrial hemp. Before I dig deep into what it is that we're doing, where we came from, where we're going, I just want to say thank you to the sponsors of this event. Thank you, New York Passive House, for organizing this. This has already been awesome. Thanks to Parsons for hosting this beautiful event, and of course, our friends at the Healthy Materials Lab. It's always an honor to be asked to speak on a panel, but when you're asked to speak on a panel and Bruce King is giving an introduction, it's an opportunity you can't pass up. If Bruce was here, I'd probably bring my new carbon architecture book and ask him to autograph it for me. For those of you who don't know, it's kind of the Bible of low embodied carbon architecture. So overall, it's a great honor to be here. So the Hempitecture story starts back in 2013 when I was an architecture student not too far away from Cornell at Hobart College in upstate New York, and actually wrote my thesis study on the contemporary relevance of earth architecture. The concept was using architecture as a pathway to mitigating climate change. We've known about this problem for quite some time. In 2013, when I was writing my thesis, I was inspired by the work of what was then Architecture 2020. I think the fact that they've changed their name to Architecture 2030 encapsulates that we've known about this problem for a while. We have a lot of work to do, and we're just getting there now. But I'm really excited about the progress that we're making. Companies like Mats that are bringing wood fiber insulation to market. This is representative of the new interest that we're seeing, as well as the awareness that is helping bring these products to market. So we need to keep making progress. And I think that's why we're all gathered here in the room today, to keep making progress on this challenge. Overall, Hempitecture exists at the nexus of innovating carbon negative materials derived from industrial hemp and natural fibers, ultimately storing carbon dioxide. It has certainly been a long journey for Hempitecture, starting out in 2013. I'm going to talk more about our manufacturing process and our products. But before I get there, I just want to point out, we're hearing about a lot of solutions today. We heard Bruce reference straw and different ways of approaching concrete and mass timber and wood. There are lots of different solutions out there. So we represent just one of the many solutions that I think are going to be important for us transitioning to a regenerative bio-based building stock. So I'm often asked, why hemp? Why not cotton, flax, wood? We, in particular, Hempitecture, have selected industrial hemp as our primary ingredient for a number of reasons. First, I just want to provide a note on what industrial hemp is and what it isn't. I get asked quite a lot, what is going on with hemp? This is a uniquely American concept. I'll point that out, that we confuse industrial hemp with recreational or psychoactive cannabis. This confusion dates back to the 30s. It's tied to systemic racism, competing industrial interests at the time. And this stigma, to some extent, it still exists today. It's important to consider that before industrial hemp was banned in the United States, it was used extensively for rope, textiles, a wide range of materials. No, industrial hemp will not get you high. The reemergence of industrial hemp in the United States is for its fiber, it's for its stalk, and it's even for its nutritious seed that is rich in omega-3 fatty acids. So a few benefits there. It's an agricultural commodity that is grown in large-scale acreage, similar to a crop like corn. Today, we're just relearning this American heritage that we had that was once deeply connected with industrial hemp. But there's a special reason why industrial hemp works so well for building materials. It's rapidly renewable. It can be harvested in a 4-month cycle or less. Compare that to other materials that have much longer life cycles before they can be extracted. It can be grown with very little water or pesticides, although it does prefer water. It can be grown completely dry land, but it also has soil regenerating qualities. Industrial hemp has an incredibly deep root structure that reaches down and it breaks up compacted layers of soil, ultimately restoring that soil quality and returning nutrients back to the soil. When we talk about the decarbonization of the built environment, Hempitecture's perspective is not that we just need low embodied carbon materials. Low embodied carbon materials are great. It's that we need to get our materials from ingredients that do more for the earth. Hemp is a crop that does that. It's improving land, it's regenerating soil quality. It's being used as a rotational crop, which is increasing yield on land that is growing food commodities. You may have seen those bumper stickers. I think they're green. They say no farms, no food. It's true. Just as our buildings are contributing to our climate crisis, The climate crisis itself is contributing to food insecurity, decreased yield, drought. Hemp is just one of the toolkits in our toolkit that helps address these issues. So beyond that, the other reason that we really love using industrial hemp as a building material is that it's particularly adept at capturing carbon dioxide. 1 acre of industrial hemp can offset about 9.8 tons of CO2 per acre. And this is going to vary depending on your soil quality, your location, climate. But this summer in Montana, I was at a field that was grown particularly for our insulation. A 500-acre plot, some quick back of the envelope math here. That's 4,900 tons of CO2 in just one field alone. So what do we do with that fiber? We take it from the field after it's been primary processed, which means separated out from the other plant parts that are less useful to us. And we turn it into building materials, primarily thermal and acoustic insulation products. I brought some samples here today. So later on, happy to talk more, share, see it, touch it. We built a manufacturing plant in the agricultural heartland of the Rocky Mountain West, where we convert that fiber into these high-performing, low-embodied carbon materials. Our facility is brand new. We're still getting up and going. We're gaining code compliance with all of our different products, but we're really optimistic about the future that's in front of us. If anyone tells you that manufacturing is easy, they're lying, I promise you. I'm sure Matt can relate to that. Our factory is powered by 100% renewable energy. We opted into a program to source all of our energy from renewables. So we are certainly paying a little bit of a price premium, but I think that goes to highlight the lens in which we're approaching this. It's a holistic approach where we're using energy that's renewable to create low embodied carbon materials. We're actively conducting life cycle analyses on all of our products to quantify the carbon footprint that goes into each of our products. And ultimately, we're going to move down the road to getting an environmental product declaration. I'll share a little bit more about our carbon data coming up. So I'm excited to share a little bit of an under the hood look with you all, because this is a trusted audience of friends here, about what we're coming out with in the future. We started off with our flagship product, hemp wool insulation, 92% hemp fiber, non-woven material used in cavity construction. But now with our manufacturing facility, we're really able to start to diversify our product offerings. We're going into rigid continuous insulation, loose fill insulation, underlayment products, acoustic products, a whole wide range. We do believe that our products could be in the skyscrapers of the future, but we have a little bit of ways to get there, and we're going to talk about how we get there. As any of these panelists can tell you, bringing new products to market is challenging. It requires a lot of capital, a lot of research, a lot of development, and we're well underway with all this testing that needs to happen. So that we can bridge the gap between the primarily residential markets that we're serving today and bring our materials to urban centers like New York City. So a bit about our products in particular. So Plant Panel EXO, it's a rigid continuous insulation product. And then we have a few cavity types of cavity bat insulation. As architects and designers, technical specifications, they're a big part of why we choose certain materials. Probably two of the most important features are thermal resistance and fire resistance. With our manufacturing technology, we're taking that agricultural commodity, that hemp fiber, and we are refining it as much as possible to extract higher thermal performance in our bat materials. We're ranging from R 3.4 per inch to R 3.7, depending on the product, which is comparable to a lot of conventional insulation. And our rigid board is coming in at 6.5 for 2 inches. For fire resistance, this is a big deal, and this is something that we've invested a lot of time and resources into looking into non-toxic, bio-based fire retardants. I think it was mentioned by a previous presenter that fire retardants present hazard within our environment, and oftentimes they're invisible. And so we have sought a wide array of different fire retardants and tested them to be non-toxic, bio-based, and safe. And we're really excited with the preliminary results that we're seeing. We've got Class B flame spread coming out for both our board and bat insulation products. And we're ultimately working towards a Class A. When we talk about bringing materials like ours, bio-based materials, into a setting like New York City. Class A really is the standard that we need to get. And we have a pathway to get there. I think that pathway of getting there is exciting because we can imagine a future where our materials are lowering the embodied energy and embodied carbon of buildings in our built environment. Beyond product performance, which maybe an architect might be looking at, I think there's another important element that we should talk about and think about here, and that's the health and sustainability elements. Earlier, I showed a picture of a family installing hemp wool insulation. We're making materials that are safe to touch, safe to handle. They won't irritate your eyes, skin, lungs. I'm not sure that you would ever see a photo like that of a family installing mineral wool or fiberglass insulation. And if you do, they might get reported because those materials are nasty, they're itchy, they're irritating, and they're filled often with toxic chemicals. In regards to decarbonization, as I mentioned before, we're still working through our life cycle analyses and moving in the direction of product declarations. But we see that 5 cubic feet of our batt insulation is offsetting over 2 pounds of carbon dioxide. Compare that to mineral wool, that same amount is emitting over 10 pounds of carbon dioxide for every 5 cubic feet. So here's another performance metric that I think is kind of value added in some senses, but it's really important. In New York City, we're bombarded with sound. There's horns, sirens, people, planes, helicopters. I live in Idaho, by the way. And so being back in New York City, it's a little bit of a sensory overload for me. But our homes and environments, they should be sanctuaries. They should be places that we can go, we can recover, we can get some reprieve from that sound that we're often bombarded with and disconnect from the world around us. Acoustic comfort plays a huge part in that. So we did some recent analysis on the acoustic performance of our products at different frequencies. Looking at the curve of frequencies is important because this curve reflects the wide range of sound that we might experience in our world. Plant panel, our rigid continuous insulation, has performed extremely well at certain frequencies, absorbing 99% of sound. With the batt insulation, that's at a lower density, also performing well with one product absorbing 90% of sound. Comparing this to wool, which is another natural fiber, absorbing 79% of sound. So this all adds up to enhanced comfort, which is how we experience our built environment. This is all at a 2-inch thickness. So earlier in my presentation, I said we need to keep making progress. It's true, we really do. But I firmly believe that we're on the cusp of some really exciting transitions within the built environment. I think that this transition is beginning to embrace bio-based materials in lieu of synthetic, toxic materials, and we're bridging that gap. Think of a field under a blue sky that's absorbing sunlight and restoring quality, soil quality. This field is taking carbon dioxide out of the atmosphere. It's bringing dollars to rural economies. It's empowering the next generation of the family farm. Now envision our world built of materials of concrete, steel, and glass. These are materials based on extraction. At Hempitecture, we're working really hard to bridge this gap between this world of extraction and instead embracing a world of rejuvenation. Through using hemp as a building material, we're rejuvenating soil quality, we're rejuvenating our existing environment with materials that add thermoacoustic comfort and with materials that restore our balance between the built environment and the natural world. So that's our mission at Hempitecture. It's an honor and a pleasure to share it all with you here today. And I look forward to chatting more this afternoon. Thank you.
So real excited to show you what we have got going on here. I'm assuming that, okay. What we produce is a ground glass pozzolan. It goes by the trademark name Positive, but it's amazing. It's basically generated and derived from post-consumer recycled glass, curbside recycled glass. New York City alone generates collects about 78,000 tons of recycled glass here in the city, and we take a percentage of it. This was a big changing point for us. Basically, that's the Hallett's Point project in Queens with the Durst organization. They've been very supportive of using the material, and every aspect of that building was an example of its use. So there was done in conjunction with the City College of New York School of Engineering, and they had embedded curing centers and such. It was a very intense thing. This is going back in 2016. So yeah, this was a changing point for the material, and this is what now catapulted us to where we are today with a full-scale commercial pozzolan plant. It's the material's safer. It's an amorphous silica, not a crystalline silica. It's post-consumer derived, and it's that perfect circular example of taking regionally harvested recyclables, processing them regionally into a pozzolan that goes to a concrete producer that produces the concrete that goes back to the region from which the recyclable was derived. So it gives you that perfect circular example, as well as dramatic reduction of the embodied carbon for concrete. Pozzolans have been used for literally thousands of years. Glass is very similar to volcanic ash chemically. It's about 72% silicon dioxide chemically. So, and it's very consistent. Soda lime glass in Rome or in Paris or in Miami or in Los Angeles or New York or Boston, it's very consistent, has a consistent level of silicon dioxide. So, and that's what makes it a good pozzolan. The Romans used the calcium carbonate or limestone, and they blended it with the volcanic ash from Mount Vesuvius, basically to make their examples of ancient Roman cement, which is pretty similar to what this material does. In the end, it's more durable, stronger, and makes a more resilient concrete and extends the life cycle of that concrete as well, which I'll get into in future slides. And basically how it works is just like any other pozzolan. During the calcium silicate hydrate reaction, there's two products are formed. One is calcium silicate hydrate. That's the bonding agent that bonds the aggregates together. And the second is calcium hydroxide, which actually creates porosity in the concrete, which is deleterious to concrete. What happens is because ground glass pozzolan is an amorphous silica, the silica atoms are loosely bound, they're not tightly bound like a crystalline silica. And during that calcium hydrate reaction, the silica atoms split off and bond with the free calcium hydroxide to create more calcium silicate hydrate, or more bonding agent that bonds the aggregates together. So it makes a more durable, stronger, more resilient concrete. And as does many pozzolans. And some of the challenges that we face here in the recycling industry, that's this mound of glass you see in the picture reflects what we get in our plant. When you put your glass out on curbside, it's mixed in with paper, plastic, aluminum, and ferrous metals, and basically in glass. It goes to a material recovery facility, or a MRF. Those are all regional. And then the MRF brings it to us. And basically the MRF sorts out, they do a pretty good job. They get it to about 80% glass by weight and 20% non-glass. So we have to take that pile, basically, that you see here, and that's what we get as our feedstock, and create a feedstock for our positive or ground glass pozzolan that has a percentage of loss of ignition of below 0.5%. As ASTM C 1866 prescribes. I was one of the authors that was spearheaded by Amanda Kaminsky of Lend-Lease, which was she was an enormous help with getting that done. So through that standard, we created an understanding on how to process post-consumer glass into a pozzolan, and creating consistency and quality in the product. So that was a big changing point. And that was published in one of the only good things that came out of 2020, in April of 2020. So at any rate, so here's the other dilemma that we face in the concrete industry and the cement industry. all of the coal-fired steam electric generating plants have been closed in the Northeast. So if you don't burn coal, you don't generate fly ash, which is a good thing. In the end, you need pozzolans, and fly ash was probably the most commonly used pozzolan in the industry. You need pozzolans to create high-performance concrete. And that goes back to that crisis that we have in terms of reducing the embodied carbon by replacing the cement in concrete. Cement is a big culprit of embodied carbon, right? So what's happening now is a lot of these structures are being built with cast-in-place concrete. You need high-performance concrete to make these cast-in-place structures. And then, you need pozzolan to make the high-performance concrete. So you have the demand for pozzolans going up and the supply decreasing. So we feel that ground glass pozzolan will help bridge that void. And then you think about another supplemental cementitious material, which would be slag. Slag is generated from the purification of iron ore into steel. 90% of the slag that we use here in the country is imported. On the East Coast, it comes from France, Turkey, and Brazil. On the West Coast, it comes from Japan and China, basically. There's others as well, but so it's not regionally or domestically derived. It's imported, and the fact of the matter is that a lot of these steel manufacturers are switching over from blast furnace manufacturing process, which generates a slag, into electric arc furnace that really doesn't generate any usable slag. And they're doing that to reduce their carbon emissions as well. So what's happening is you're getting a decrease in supply of slag, and you're getting an increase in the need for it. So again, we feel that we have something that is going to help bridge that void. So what we have is absolutely the opportunity to create that perfect example for the circular economy. We take a variety of glass recyclables. It doesn't matter the color. It doesn't have to be color sorted. So we take curbside recycled glass, take it into our plant, we process it, and every step of that process has a chain of custody for it. So there is an absolute transparent chain of custody for our product. We take it in, it gets curbside recycled, it goes to a material recovery facility. Everything is documented. We have to have it documented because of our various permits that we have, federal air permits or state air permits that are federally mandated, and every aspect of the process. So we take in the glass, comes in, it gets weighed, gets tipped into our tip floor, gets weighed again, so we understand the volume and weight of that glass that comes in. Then we have to separate out all of that other non-glass component. So we further recycle materials out of that, and some of it goes to trash, but everything is accounted for. There's a weight and a ticket for everything. There's a chain of custody, a transparent chain of custody for our process. Then we transform it into that white powder that you see there, and that goes then, it gets loaded into a pneumatic cement tanker, goes to a concrete producer. It gets batched in that from that concrete producer, and there's a batch ticket that's derived that shows the amount of cement that's displaced with the use of a pound for pound equation of the ground glass pozzolan. So in the end, you have that chain of custody with regards to the manufacturing. That yard of concrete in that concrete mixer then goes to a project, and it gets installed. So you have it from beginning to end, a perfect, transparent chain of custody for the material. And why is that important? Well, Harvard University, Harvard Business School, just did a course study that every new MBA student has to take. It's Urban Mining Industries. It's Harvard University and Urban Mining Industries, decarbonizing the supply chain. You could buy it at the Harvard Business School store. It's inexpensive. That's just something that I have to. In the end, basically, they realized that carbon offset trading is coming to the U.S. Creating carbon credits is important, and adding value to that carbon that's being offset is critical. And having the transparency in that carbon offset is what adds value and gives an understanding for the actual carbon that's offset in a project. By the way, that's the New Canaan Library up in New Canaan, Connecticut. That was done with a Turner Construction Company, and all the concrete used for that was with the 40% positive replacement. This is an understanding of the amount of cement that's used in the United States, about 100 million metric tons, 120 million short tons. So basically, the increase in the need for concrete is obvious with the way that we're building with concrete. Concrete is critical for urban construction. It's fire resistant. For the resilience of the materials is amazing. The speed of construction, and so on and so forth. So it's a very good material. How we use our cement to make our concrete is critical in reducing the embodied carbon. And give you an idea, this was done, I presented to MIT about 12 years ago. It's crazy how fast time is going. But basically, this was given to me by MIT. Cement reflects about 10 to 15% of the overall mass of a yard of concrete. And yet, depending on your compressive strength, the mixed designs and such, and yet it reflects about 80% of the carbon emissions associated with that yard of concrete. So it's very important how we use our cement and our cementitious materials, right? So with ground glass pozzolan, it's a pound for pound replacement up to 50%. And it depends on what you're trying to achieve with your mix designs, right? So there's that opportunity, and there's opportunities to create ternary blends. That's a mix with other pozzolans or other supplemental cementitious materials. We're actually going as high as 70% with a 35% replacement of with positive, 35% replacement with slag, and 30% of OPC. So big opportunities to really create dramatic carbon reduction for concrete. This is really a cool slide by the Oregon Department of Environmental Quality. It's not me, this is all third-party information here. In the end, this really does show or highlight how the use of glass is the highest and best use for recycled glass when you're using it to replace cement. People normally think that bottle-to-bottle recycling is really the best way to go. Well, with regards to reducing the carbon footprint, the reality is it takes 6 tons of bottle-to-bottle recycling to save 1 ton of CO2. It only takes 1 ton of cement replacement to save 1 ton of CO2. Only 1 ton. It's amazing. So here in the United States, we about 12 million tons go to land, are generated. About 3.5 million tons actually get recycled into bottle of fiberglass. So there's about 8.5 million tons that are left over that can be used to create ground glass pozzolan to replace cement. There's a big opportunity. That's a picture of our plant down below with the 2 big ball mills. So very good study. Another good benefit of it, when you take mixed glass, mixed recycled glass, clear, brown, and green, on an average, about 60% of MRF glass is clear. And then the others are mixed between brown and green. When you mill it, it becomes bright white. On a scale of 1 to 100, it's about a 90. So it's extremely white material. So this is some, what you see on the left-hand side of the screen is sidewalk slabs that were done with New York City Department of Design and Construction and New York City DOT back in 2016. This picture was just taken this past year. 40% replacement of glass. You can see how bright white that is. A 30% replacement of cement. with fly ash, and you can see that white pad that was dropped on that slab, and then a 20% replacement down below. These slabs are 7 years old. They look great, and you could see by creating a higher solar reflectance for that gray concrete mix, you're reducing heat island effect non-roof for the urban center. That everyone benefits from that. And that's something that's critically important as well for urban infrastructure. This was mixed design that was used at the Durst Organization project at Hallett's Point. It was the example that was used for our LCA, life cycle assessment for our material. We had a company called Climate Earth came in and did an assessment of every aspect of our production. They took into consideration how our electricity that we use is generated, whether it's from hydro, nuclear, or coal-fired, natural gas. All of our electric consumption from every motor, all of our emissions, and how we separate out the non-glass as well. Every aspect of our production was taken into consideration. So what it yielded was an understanding that we're only 5% of the global warming potential of the cement that we're replacing pound for pound. Well, if you think about it, this was a 50% replacement of the cement in this 9,000 PSI mix design that was used at Hallett's Point. You can see we made strength. It creates additional compressive strength because of that calcium silicate hydrate reaction and the calcium hydroxide bonding with the silica. In the end, we create more higher strength. We reached our goal at 9,600 PSI for a 9,000 PSI mix. And at 56 days, we're approaching 13,000 PSI. So an amazing benefit. You're increasing compressive strength, and there's even a bigger benefit. This is an interesting study that was done by City College of New York School of Engineering. This measures the rapid chloride permeability, ASTM 1202, and it's an electric charge that goes through a beam, basically, that's made batch with positive or ground glass pozzolan, excuse me. It just shows the what cement only is, and the lower the Coulomb level, the better the resistance is against chloride ion attack. So why is that important? The embedded steel in that concrete does not get corroded. You want to reduce the Coulomb levels for your concrete. This is going to help increase the life cycle of concrete used for infrastructure. Anything that's exposed to chloride ion attack with seawall, anything. So if you think about it, you could see we're orders of magnitude better than straight cement, than slag, than fly ash. And it's a great opportunity really to use that ground glass pozzolan for that. With regards to compressive strength, it quickly catches up to straight cement in the mixes as well. And it continues to grow in strength past 90 days as well. With regards to freeze-thaw studies, again, this was done by City College of New York. What you see here is 1,000 cycle freeze-thaw study, and it shows that you had less mass loss in your beam. So over 1,000 cycles, no visible cracking, no visible scaling, and that's amazing because that adds to the life cycle of that concrete. You're making a more durable, longer lasting concrete when you use ground glass pozzolan. With regards to free shrinkage or linear shrinkage, the bottom three lines that you see there are the ground glass pozzolan mixes. Reduces linear shrinkage. It also reduces heat of hydration with regards to for mat slab uses. This is the new ASTM C1866 specification. This is critical because you need to have the proper ASTM specifications to go with a product, so that the engineering community could grab onto it and use it. And, it gives guidance on the material. And it was a very humbling experience for me personally. I sit on ASTM C09, and Amanda Kaminsky spearheaded it, and she was wonderful in getting it done. And we actually got it done in 4 years. It usually takes 7 to 8 years to get an ASTM standard approved. But because we had some of the world's leading academics on our subcommittee, as well as some of the world's leading professionals in the concrete industry, it was amazing to get this done. And like I say, it was published in April of 2020. Some examples of use: the Hollis Point project, high-rise pours that went into that building, which you see in this veneer here of 10 million architectural, is way past that now. This is the Philadelphia Ballet veneer. Pre-stressed hollow core plank. Many buildings are built, and for affordable housing here in the New York metropolitan area, a lot of the MAP especially use pre-stressed hollow core plank and high strength CMU for it. So we actually have a company in Brooklyn making the high strength concrete block now, which is great. It's that even tighter circular example. So some examples of use in Connecticut. We're regional to New York as well. We're only 75 miles northeast of the city, our plant. But you see that that top left-hand building is the Connecticut Department of Environmental Energy Protection. That won the National Concrete Ready Mix Association Innovative Project Award. And by the way, Urban Mining and Positive won the 2023 Innovative Product Award at the ConAg Expo for with the National Concrete Ready Mix Association. That was a big industry validation for our work over the past 22 years. Some of the other really cool, Oxbridge Elementary School in Darien, Connecticut. I can't tell you how excited everyone is, and the kids are excited, the parents are excited, the school board, the municipality, everyone is excited about their school being built with their recyclables. We take all of, for example, we take all of Westchester County, every household in Westchester County, we get their glass. So every household in Fairfield County, every household in Rockland County, and some percentage from New York City as well. So it's really that great opportunity to showcase New Canaan Library, Torrington High School, and some really flagship applications that were used. One of my favorite stories is we worked with the Skanska Construction Company back in 2009 when they were doing the greening of the UN. We took the window glass out of the General Assembly building and the other outbuildings. We processed it into ground glass pozzolan. We gained a specification for use with the DiDomenico Civil Engineering Group. And basically it went back into the UN Plaza in the form of a permeable paver made by the Unilock Paver Company. So great, really that was the first great circular example for us. Then we, all the CMU that we use in the 10 train stations for the 2nd Avenue subway, it was specified by AECOM. Wonderful story behind that. And our current project that we have going on right now is really amazing. It's the JP Morgan Global Headquarters project at 270 Park Avenue. That project alone, this one project, is going to save over 5,000 tons of CO2. Amazing. We're about 70% complete with the concrete there. 2.2 million square feet of concrete that uses a 40% replacement of the cement and a 6,000 PSI mix design. Real excited about that. That's really a big milestone for us. And then we have another project that we just worked on with the Durst organization over at Hallett's Point. The material that we generate at our plant in Connecticut is actually going as far down to Washington, D.C. There's several projects down there that are using it. We're working with Harvard University, Yale University, and some other folks for other projects beyond, well, in the Boston market and furthering it in Connecticut and in New York City as well. But it's so wonderful to see it being accepted far and wide now. And we're actually going to be We're in the final stages of negotiations for another plant down in the Washington DC market in Maryland, and another plant for us up in the Boston market, and fingers crossed. And we're working with the New York City EDC for a plant in Brooklyn to have it, bring it right here in Brooklyn and right here back to New York City. And as you can tell from my accent, I'm not from Arkansas, right? You know, so I'm happy to bring it home, you know, and I'm real excited about that. So not that I'm from Brooklyn, I'm from the Bronx, but anyways, so, you know, the obvious reasons, the urgency to use it, you know, like Bruce had suggested, we are in a climate emergency right now, and it's something that could be done now. It's immediate. New ASTM standard, the diminishing supply of other supplemental cementitious material, and its opportunities to help contribute to lead category budgets, which is great, is many. And the opportunity to solve the problem to do with recycled glass. It creates high performance concrete. So wonderful opportunities here, and a lot of the obvious that we already discussed. So real excited about it. And that's our plant. That's our that's a bull gear and pinion gear of one of our ball mills. We just finished up the plant. Actually, during COVID, that was a challenge. It can produce about 50,000 tons of pozzolan a year. Our next second generation plants are going to be about 100,000 ton positive plants. So it's exciting, and I have to say, I thank Andre and Sarah and Allison and John Sarah and the whole group at the new school for their continued support and guidance for us, and it's really wonderful. And the architectural and engineering community is what got us to where we are today. You people are change agents, you know, the concrete industry, and I'm speaking from one in the concrete industry, you know. Back in 2006, I gave a speech at the National Concrete Masonry Association in Chicago. And I had my son with me at the time, and he said, "Dad, these people really don't like you, you know?" And I explained to him, I said, "It's okay, they'll catch up eventually." But in the end, I said to everyone in that association, and that I said, "Look, don't look at sustainability as an obstacle. Look at it as an opportunity to do good, you know, to do good business and do good for the environment at the same time. They don't always have to conflict." So I thank you very much for the opportunity to present. And any questions? Yes, sir.
The application for everything else back at the same, blend mix or not?
We're working with companies to use it in a leveling mix. You know, it can be used. Absolutely, any cementitious use can.
Basically,
Yeah. Yeah. Thank you, Brian. And I have to say, and there's no increase in cost, which is another thing. Right now, the material that we generate in Connecticut trades for the same as slag or cement. So there's no increase in cost to do this. What we need, though, is we need specifications from the architectural community, certainly, and the engineering community. So we're very fortunate that Orlando Fortunato over at Severud, and this started for me with an architect by the name of Bob Fox from Cook Fox and Rick Cook. They were the ones that really gave me the challenge to do this over 22 years ago. I was 38 years old. So, you know, a long time. The concrete industry is very slow to change. And the only way it changes is through product specifications, certainly. So I thank you very much. I'm available.
Thanks.
Afternoon, everybody. My name is Travis Ogilvy. I'm with Aero Aggregates, and we're a producer of foam glass aggregate. Andres, how do I advance this? Just got it. Excellent. So, by a show of hands, who knows what foam glass aggregate is? Okay, a few of you have. Anybody use it on a project? Okay, Felix, you're from Europe. You don't count. Excellent. So let me get into it a little bit. I'm going to tell you guys about what the material is, how we make the material, and we'll go through some applications, some uses. Similar to what Mr. Grasso is doing, we take recycled post-consumer glass and we turn it into a functional aggregate. This picture here is showing our plant and our original plant in Philadelphia. And this is the kiln line where we produce the material. So it's ultra lightweight foam glass aggregate. So we're starting with a glass cullet. So we take a glass cullet that's destined for the landfill. As they're recycling glass, they're optically sorting it. Once those particles become too small to be optically sorted, this material goes to the landfill. 96% of this material is going to landfill nationwide. So you can take the glass cullet, you could take it to the landfill, or you can do what we're doing. We're turning it into a functional aggregate and it's going directly to the job site. So the same as, again, Mr. Grasso, what we have to do is we have to clean the glass. So we take the glass from the municipal recycling facility, we receive it, the small particles of glass, and then we have to clean it, and then we have to mill it. So it's very dirty. There's a lot of organics in it. What we're trying to do is we're trying to remove the organics from the glass so we get it right back down to a pure mineral. So we look at the LOI, the loss on ignition, we test it, we get the loss on ignition to a very low point, so we have very low amount of organic material on board. It's 100% curbside recycled glass. This is soda lime glass. So we're taking the glass that's already been used, bringing it in and saving it from the landfill. So what we do is we clean it. And once it's clean, we get the LOI proper. Then we're adding a foaming agent to it. 98% of the matrix is the glass flour, and 2% is a foaming agent. Foaming agent we use is silicon carbide. We get the silicon carbide from recycled solar panels. So we take recycled solar panels, grind that material up. We have silicon carbide. Our process is a dry process. There's two types of foam glass. There's a wet process glass and there's a dry process glass. We do dry process. 98% of the matrix is silica flour. 2% is the foaming agent, silicon carbide. You can see here as we go into our kiln, so that it's heated, we go into the kiln, and much like previous explanations, we don't take the glass all the way to the melting point. We just take it to the softening point, generally about 800 to 900 C. So we're not using that much energy. So it's going through the kiln. As it's going through the kiln, the silicon carbide, the silica and the carbide separate when it gets to a certain heat signature, and the carbon separates and gives up the CO2 bubble, hence the foaming agent. We lay down a bed. It's about 5/8 of an inch thick. It goes into the kiln. In that kiln, it foams and it raises up to a bed height of about 2¼ inches. This is a picture of our cooling table. It comes directly out of the kiln, and we have no other processing. We don't mechanically fracture it. It's a cooling table and it's thermally fractured. It hits the ambient temperature of the room, and then it fractures into individual pieces. You can see these pieces falling directly off of our cooling table. And that's the material that goes into the market for use. In general, the size of the aggregate is around 1 7/8 of an inch, but it's irregular shape. So some pieces can be smaller or larger, and they're irregular shaped. I encourage everyone, I have samples in tubes outside in the lobby. Please feel free to stop by and take a sample, or at least look at a sample. So foam glass aggregate is ultra lightweight. So the unit weight of the material is 15 pounds a cubic foot. That's on average 85% lighter than natural aggregates. It's a very good insulator, has an R value of 1.7 per inch. It has a high friction angle, which means a high friction angle means it interlocks together very, very well. It's frost resistant. It serves as a capillary break, and it's free draining. One of the keys to this material is it can be in contact with water and it's not going to degrade. So as an insulating material, we'll get into one of the main applications for use for this group is subslab insulation. So this material can be below the slab because it can come in contact with the water. It can get wet, dry out, get wet, dry out. It's not going to degrade. So this is the cool part about it. Load bearing, has very good strength, which we'll get into. A couple of the uses for the material in green building applications, subslab insulation. We have an entire team of geotechnical engineers at our company that are pushing this material and sell this material into roadways, civil engineering projects. We're approved by 36 DOTs around the country and growing every day. And green roofs. Green roofs is a great application. We just delivered 32,000 pounds of our graded material to Boston for a green roof application, where they'll lay down 6 inches, a compacted 6-inch layer as the drainage layer for the green roof. Again, you're only adding 15 pounds per cubic foot to collateral load to the roof. For me, this is one of the biggest things here, that we can deliver 88 cubic yards of material to a job site. Now that's massive. If you're talking about natural aggregates, regular aggregates, you're not going to deliver any more than 22 yards of material to a job site per truck. So literally getting 4 times the material to a job site one truck rather than 4 trucks on the road. We package in bulk, and we also package into super sacks. Let's look at the thermal properties of the material. Here's the thermal analysis of the material showing the R value per inch. It's technically 1.68 R value per inch, and this is a compacted R value. So what does it do for you? Why are you using this material? Here you can clearly see it being used as a subslab insulation. It delivers thermal performance. It's an insulator. It's taking the place of XPS foam insulation, which really kind of no one wants to use anymore, right? So it's taking the place of that. It also provides incredible sound absorption. And I should talk about how's it doing that. So these individual rocks are comprised of 70% air. So if you look at the area within each one of the rocks, it's a closed cell structure and it's 70% air. So that air is doing all the heavy lifting. That's absorbing sound, it's providing thermal performance, and it does a lot of other things performance-wise. So we're displacing naturally mined aggregates. And let's just talk about that for a second, naturally mined aggregates. I think Maddie hit on it really well when he said concrete's an extracted product. We hear so much about concrete, and we're talking about Portland cement. Mr. Grasso's material is great, displaces Portland cement, excellent. Who talks about the mined sands and aggregates in a yard of concrete? 1 yard of concrete, you have that's 27 cubic feet of material. 17 to 19 cubic feet is mined sand and aggregates. So that's a finite resource, right? We just got a call last week from Martha's Vineyard, from the Island Housing Authority. They have a gravel pit on Martha's Vineyard. It's an island, right? It's running out of sand. They're literally running out of sand. They're going to have to start importing what? The sand and gravel. This is a microcosm of what we're seeing everywhere. Sand and gravel is running out. So we're taking recycled glass and turning it into a functional aggregate. Back to the application. It's a capillary break. So instead of using 6 inches of crushed gravel so the water can run laterally underneath the building, stop the hydrostatic pressure pushing up into the slab, the foam glass replaces the natural aggregate, then it replaces the insulation. Fire resistance, this material is actually a fire suppressant material. It's the best material in the world to put out a lithium ion battery fire. The applications for this material are growing almost daily, and it also contributes to lead points. Here's a very rudimentary detail about what it's replacing. Typical detail, slab on grade, a couple inches of rigid foam insulation, and then there's your gravel-free capillary break. No more, you can just put down the foam glass and a layer of Typically, I'm specifying to architects 15.5 inches. Material has a compaction factor of 1.25. You place 15.5 inches, compacted with a plate compactor, you end up with 12 inches. That's 12 compacted inches, gets you again the R 1.68 per inch. No need for natural aggregates. There's another detail showing the same thing. Again, you can put the slab directly on top, go with your vapor barrier, go with your reinforcement, and here you come with the slab directly on top. This is a project, passive house that was in Cape Cod. I have actually some pictures of it. As you can see, you can actually run it vertically up along the wall for insulation as well. Very, very easy to install. Here's the project in Cape Cod. We deliver in super sacks, and it's very easy to place the material. You're swinging it into place with a bottom dump super sack and placing the material. Again, you can see the pipes and different interferences there. It just flows in around it rather than trying to cut rigid insulation. And again, we're talking about an insulation material that can be in contact with water and still perform and not degrade. So here's the project completed in a compacted layer. I'm just going to run through some projects so you can see that this material has been in application for a long time. In Europe, as Felix can attest, there's multiple manufacturers of this material. In the United States, there's only 2. We're one of them. This is a project in New York City. Again, existing buildings, when you have to fill existing buildings and you're worried about existing collateral load, this is the material because it's only 15 pounds a cubic foot. Here's the finished floor. The finished floor is directly on top of the foam glass aggregate. This is a project in Washington, D.C. Again, a shot from my geotechnical colleagues, but we're talking here about reusing material. So I just got to stop and tell one story about a recent project. I think it was 2 or 3 months ago in Philadelphia, a fuel truck caught fire underneath a bridge deck on I-95, and the I-95 bridge collapsed. The solution from PennDOT, because we're in Philadelphia and we're working with PennDOT all the time, the solution was to use foam glass aggregate to rebuild that bridge. They used MSE, mechanically stabilized earth walls, in 2-foot layers They built that bridge back up 22 feet and then repaved and opened that bridge in 12 days. 12 days it was opened up. But the cool story is in about 30 days, they're going to start to deconstruct that layer because they built it from the outside in with the real steel in the correct way. They will now get to the middle and they will deconstruct. They will take that material and they will bring it over to another job and reuse it. Absolutely, you can reuse the material, just take it right back out and reuse it. That's geotechnical application. This was a cool project. It was in Camden, New Jersey, at Hilton Garden Inn. This is down along the pier where they have very soft soils, and they had to bring up the grade for this building 4 feet to put the slab. So 4 feet of conventional aggregate or soil would be too much load. So here we're using foam glass aggregate, and with all these interferences and pipes coming through, very easy to work with. Another project in New Jersey, again, sub-slab insulation. Boston, Massachusetts at Logan Airport. I don't know if this is in a form of an MSC wall. This is a RICO wall. You can see the metal straps are tiebacks, and that actually holds the wall in place. We just did a job in San Francisco in Mission Rock, San Francisco, again, along the pier. And we have soft soils. This is a great application for the material. Project in New York at the United States Tennis Association. Again, they chose the material here because of all the communication cables and conduits running in the project. And again, foam glass aggregate was the choice. Another same project, Hilton Garden Inn. I want to talk quickly about the graded aggregate. So now what we're doing is we're taking the larger pieces and we are sizing these materials down for use in concrete. So again, if you take a yard of concrete and you have 19 cubic feet of mined sand and aggregates, you literally can take that material away and you can replace it with a graded aggregate. So this material is 100% recycled content, displacing natural aggregates. So where are you going to use this material? So different sizes, the finer particle sizes are going to go into dry mortars. Our friend back there was asking about self-leveling underlayments. Of course, you can use it in self-leveling underlayments. Different types of dry mortars, stuccos, GFRCs, engineered cementitious composites, tile adhesives. As the sizes start to go up, now we can go out of mortars and into concretes. We can go into ready mix, precast, dry cast. And this material recently this year, we just got our ASTM 330 approval. So foam glass aggregate is now approved as a lightweight aggregate for use in structural concrete. And then, of course, as these sizes get bigger, as the particles get bigger, you get a little bit more insulation value and the unit weight goes down. The particles get smaller, the unit weight goes up a little bit. But at the bottom here, you can see no matter what product you're using it for, it lowers the unit weight, it improves the insulation properties, it absorbs sound, and it's 100% recycled content. So if you're going for lead points, this is the material. And I just want to point out the structural integrity here of the material. So what we're looking at here is these are mixed designs that I did in my lab to test out the strength of the material. There's no natural sand or aggregates in these mixes. And you can see here the compressive strength values over 4,000 PSI. And I would point out Mr. Grasso, sets number 2 and 3 have the positive material on board. It displaced some of the Portland cement. So you can see the 56-day values and you can see the jump from 28-day to 56. And that's really a testament to the positive material. But you can, my point here is that you can make structural concrete with 0 mined sands or aggregates using recycled glass aggregate. Probably the coolest thing, the performance attribute, I should say, is the thermal performance here. Because of the R value 1.7 per inch, if you introduce this into the concrete, you greatly affect the thermal performance of the concrete. So this is one of the structural mixes from the previous slide. And you can see here the R value. Now, standard concrete has an R value of 0.08, pretty much negligible. By adding the foam glass aggregate, I've changed the R value to 0.54. Now, if you do thermal modeling based on that, it's a game changer. It's completely different. So as far as passive houses and a really great detail, if you put the foam glass aggregate below the slab, then you put the graded foam glass aggregate in the slab, in the ready mix, you will now have sub-slab insulation, now you have in-slab insulation. It's the perfect scenario for good performance. And just a testament to show, it's just one of our customers that are using the graded aggregate in a CMU block. This is a company up in Maine making a comfort block system. And he's got 60% of his sand and aggregates have been displaced by foam glass aggregate. And he's still meeting the requirements of C90, right? So the CMU block still meets all the strength performance requirements of C90. He's literally taken 60% of the sand and aggregate away and replaced it with 100% recycled glass aggregate. Just a few case studies I would point out. We have a number of case studies on our website. This was a case study. And also to point out how long we've kind of been at this in the civil engineering market. This was 2018. We did a project with at the Subaru Technical Center. Here's another one. This is a tunnel infill. This is a really cool application. When you have existing buildings, old infrastructure, and you're trying to bring them back, a lot of times you rip things out, you need to fill. This is an incredible material to fill. So they were literally filling tunnels before they continued to reconstruct this building. So a great opportunity to place recycled material. And then finally, the Tennis Association building. Again, you can see in section there how much material they're able to place. That's my story, and I'm sticking to it.